I accept the late submission if the GA does not grade yet. Okay, which means, however, that doesn't mean you can submit later. So you can submit the SEDs first, on time, and if you modify or revise your submission, you can contact the GA whether GA grade your submission or not. If not, you have a chance to resubmit. Okay, otherwise, you will get the late penalty. So do not ask to extend the due date first. Okay, and also I usually like to have a demonstration for your project. I did the last semester, but this semester I had 70 students, so it's not possible or easy to have a demonstration. I mean the public demonstration. The GA will have the individual demonstration after the class by assigning the time, but not for the warming up project. Warming up project, nothing special. It's for the reminder and those who do not have experience on such a program. It's a time to get used and learn. But for the project 1 and 2, I'm thinking the first individual demonstration with the GA, then GA will select some of the good, also bad example of the submission. Then we'll have some selected the present demonstration in the classroom. Then we can share with the others. Okay, so. We are going to continue it's already chapter 5. So if you check the textbook, we already covered a couple of 100 pages already. So which means whenever, even though I do not assign the reading assignment or the reading material, but it is your responsibility to read. And for the preview, I don't expect the preview of the class, but at least the review of the class. The best way is reading the textbook. Textbook include everything. And if you need more information, the textbook has reference pages. So you can use the reference page to find the more detailed information about the contents or the topic or the algorithm. Then if you need more information or are not sure, sometimes it's hard to understand the description in the textbook, then you can find the online material and the other textbook. Also, that is the best way to learn. Do not rely on the PPT file only. This is just a summary. So it's the supporting material of the lecture. So it doesn't. I cannot include each and every detail. Even my lecture, I try to explain the details of that, but I couldn't cover some of the details or precise topics. So it's your the responsibility to catch up such a thing. Okay, so we are discussing about the synchronization problem. Since we are able to create the processor to manage your system using the operating system, the software. So one of the main jobs of the operating system is to create and operate and manage the processes. Only one process? No, we have the multiple processes. However, we have the very limited resource and also limited the data, shared data. So that causes the problem of the race condition and synchronization problem. What if we have the one common data but accessed by the multiple processes? Then we cannot guarantee the output. So to address that problem, we have the solution of the the operating system use the process model like the critical section. Okay, so critical section, entry section, and exit section will be provided to when a process access the critical section. Critical section means to the update or delete or read the shared data. Okay, so that is the typical. This is the typical process model. Depending on how to define the entry section, exit section, there are several algorithms. So throughout this chapter, we will discuss about such a algorithm. We can first we define what is a critical section problem that satisfies these three requirements. So it's obviously only one process can access such a critical section, so otherwise it will be mixed up. So it will cause a problem. So progress is, even though it's explaining what define the details, it can be summarized as deadlock free, which means eventually one of the processes will enter critical section. There is no deadlock. Based on the entry and exit section algorithm. Okay? Then the bounded, this is for each process. One process will enter the critical section, bounded waiting. Those who want to enter, those who want to use the shared data, they will eventually enter the critical section. It's a bounded waiting. So for all the process in the entry section, these three are the requirements of the critical section solution. So there are three types of the solution. One is the software, as we learned, algorithm 1, algorithm 2, Patterson solution, and so on. These are the we implemented such an entry and exit section using the software code. So that is the software solution. Most of the software solution need a busy waiting. Why? In the entry section, we have a while loop. That causes a lot of. What is the problem of the busy waiting? It causes a lot of CPU cycle. So it's a waste of the CPU resource. So that is one of the problems. So we have another solution using hardware. Hardware solution means instruction using test and set and swap. We use such a hardware solution. Then today we are going to discuss about the operating system solution. Operating system solution means operating system provides a certain data structure, okay, to address the problem of the critical section. However, most of them is basically we can understand the critical section problem as the getting the lock and release the lock. Okay, so that is software solution, hardware solution, operating system solution. We can basically understand getting the lock to enter to access the shared data. Then after that, the release the lock. Then depending on how to select the process from the entry section, there are different algorithms. Some of them satisfy with the requirement, some of them are not. Okay, so we have seen the algorithm 1, algorithm 2, and Patterson solution. Patterson solution satisfied with the 3 requirements. However, this is for 2 process cases. So, but still, even though we do not use the Patterson solution directly, but that's the fundamental idea of the all other the critical section solution. Okay. So using hardware, so we have seen the test and set and swap. So using that one, we can address the problem. So today we are going to discuss about the operating system based solution and some examples in the operating system. Yesterday I pulled out this one using the string, then it's broken, so I cannot use that. So the headset or the earbud, so it has a problem on this. Even I returned there's a record of the surface, the adapter, that there's a problem in here. It's a connector problem. So I ordered, but I don't know whether that fits to this one. I tried. Can you hear the sound? I tried my best to get close. Okay, so what is the semaphore in terms of a dictionary? Even I didn't know that, the definition of the semaphore. I knew the semaphore in operating system or computer, but I didn't know semaphore actually means such a visual signal, like using 2 flags when actually semaphore was used in military. So in the military, so actually I was driver. My specialty in my military service, I was driver. So I have driven for 2 years. So usually the camp is for the microwave communication. So most of the soldiers in my camp, they are actually in the top of the mountain. So microwave communication is directly. So there should not be the block for communication. It's very secure because it's a microwave. The problem is we need to support provide all the supply, and in case of something, the vacation or something happen, family matter, we need to drive up to the 6,000 feet mountain. So even winter or whatever. So also next to my camp there was another there's I don't know exactly the name of that military group, but there's a tank. Okay, so they usually use the hand signal using the flag, whether this is left, the target is left, or target is right, or the far away. They are using, even for the number, the specific the signal, the protocol. So this is called the semaphore. Okay, so semaphore can represent all the alphabet and the number. So we can use such a name of semaphore to address the problem of the critical section. How? What is the relationship? The semaphore here and the critical section problem. We can give the signal information to the process whether this shared data is used or not. So we will see what is a semaphore. Semaphore is the data structure. Okay, data structure for what? It has an integer value. So inside this semaphore structure is definitely atomic. Okay, which means if this one is used, it should be complete or not. Okay, it cannot be the interrupt in the middle. So this is the atomic, the data structure, and it has only integer value inside. That is the S here. So this data structure has only two operations. There's a specific meaning of the P and V is in Dutch language, Netherlands, but I cannot remember. But it's usually use the P and V. P means it's a weight, and the V is a signal. Weight means it's in terms of the lock. So I'd like to getting the lock. Okay, so I'm waiting to enter the critical section or the whatever is a weight. So at that time, so the value of the integer value is decreased by 1 by the operation of weight. And another operation is a signal. Signal increase that integer value is a +1. There are two operations. Okay. Then how we can use the data structure? So we can manage how many processes. Okay. How many processes are waiting for to enter the critical section. Then this one I'm leaving. When I'm leaving, so you can increase the value. So highest value means it's a nothing. Okay, nobody wait, and 0 means it's the full of the processor. We can understand such a way. This is the data structure provided by operating system. So we can use such a semaphore to address the problem of the critical section. There are only two operations. Keep in mind. Well, sometimes I got confused which one is weight, which one is the signal. Think about I'd like to enter critical section. To do that, I need to wait to give the information signal. Then I'm going to wait. Okay, so I'd like to get the lock, acquire the lock. Okay, and the signal. So I'm leaving. I'm done. So I'm going to signal to others. I'm done. So those who are willing to enter critical section, they can get the alarm. So we can use such a semaphore for the synchronization tool. There are two types of, actually basically the same, but depending on the number, this S value, there are two types. One is the counting semaphore. Counting semaphore is the arbitrary integer number. Okay? While the binary semaphore is the S is 1, which means 0 or 1. If nobody nobody uses semaphore, its value is 1. If somebody wait is -1. That means the 0. Okay? Then it's used. So such a binary semaphore can be used for directly lock. Okay, so because of that, this binary semaphore is called a mutex lock. Either it's a mutual, so it's a mutex lock. Mutex lock is used a lot in operating system. Long time ago, when we used the Windows 95, Windows 3.1. So from time to time, so there's a pop-up from the operating system, Windows operating system. It's a mutex. The mutex, the lock problem, or it cannot handle, it cannot find the mutex lock problem a lot because of this one. So this one is the mutex lock used a lot to address the problem of the synchronization, critical section problem. How do we use this mutex lock as the lock key? Okay, yes?
Why is it called the mutex lock, since we have difference between a mutex and a semaphore?
Oh no, actually the mutex is the special data structure of the semaphore. In case the value is only 0 or 1, okay? Then the only difference is this value, S is the arbitrary integer or the 1.
But for mutex, the weight and signal should be from the same thread of the process.
Yeah, it's the same thing, same operation.
In semaphore, it can be from the different process and different.
It can be, but it's basically the same. Actually, the mutex is from the semaphore data structure. Okay? So, how can we use? Just a simple. We can use the weight operation for define the semaphore. Okay, so it's the initial value is usually 1. 1 means it's nobody used that. Okay, then if we send so in your program, if I need to access the critical section, then operate the wait signal, which means that S is set as the 0. 0 means if the other process or thread would like to enter the critical section, but they cannot wait because it's already 0. So as you can see, it's while S is equal or less than 0, you can the while loop cannot use the semaphore, the mutex. Okay, so it's very simple. However, it still requires, for example, if somebody uses, so you need to busy waiting. It calls the busy waiting or spin lock. Spin lock is it's kind of a lock. It's a spinning. It's an infinite loop until the other process and the signal the operation. Okay, so it's still calls the busy waiting, like the software solution. Okay, so this is I copy and paste from one of the Java program that used the semaphore. So we have the 3 functions. The function, one is a print, another one is a random function, this one is sorting function. We regard that the code need to access the critical section, which means the shared data. Then in your program you can define the semaphore, okay? Then send the semaphore wait. So semaphore wait is the same as the wait. So depending on your API, the system library, the name may be different. In this case, it's a semaphore wait, and my semaphore will be a wait signal. Then you can do you can enter the critical section. Then you can release my semaphore. Then the other thread, especially for multi-threading program. Okay, in your multi-threaded program, is from you can. In this case, it create the 10 thread. When they use this function that require the shared library, so you can use the semaphore to control to address the problem of the synchronization using binary semaphore or mutex lock. Okay, so we can use such in your program. Okay, so in your program we can use the wait and signal. Okay. One of the problem of using such a semaphore with the wait and signal is still cause the busy waiting. However, that doesn't mean it's the worst. We cannot use it. So still, it's simple. So if in case in your program or the program, if that doesn't need the critical section is not accessed a lot, or takes a lot of time, So which means there are not many thread, not many process direct enter critical section. So busy waiting, in case busy waiting is not the serious, you can still use such a the simple mutex lock for the synchronization problem. Okay, so not always the busy waiting will cause the problem. However, if that happens a lot in your the multi-threaded program, you need to think about the different way. Okay. So to address the problem of the busy waiting, what can be the solution to address the problem of the busy waiting? Busy waiting is caused by the whenever wait signal is caused, it tries to check the whether the integer value is available, whether this is a 0 or not. Keep checking, right? Because it's a keep checking, that causes the spin lock, it's a busy waiting. How can you address that problem? Instead of checking, why don't you? So, for example, when you wanna see me in my office, so Professor Lee usually closes the door when the Professor Lee is meeting other students. You keep checking the door. That is a busy waiting, right? Every minute, every second. Instead, if I put the waiting room, okay, you don't have to check, just wait in the room. Then if I'm done to meet one student, then this student or my secretary will inform to the waiting room. Then next. So that is the same, the solution here. Instead of the while loop, we can keep a list of the process inside. So this is a waiting, the room waiting queue. So we can manage the wait queue. So waiting doesn't mean the wait, the operation is the process who are waiting for that the semaphore. So we have the another two operation. One is a block. Block means when we have the new student to the wait the queue, okay, waiting room. Then another one is who is the next wake up from the if they are sleeping, we need to wake up the one of the student from the waiting room, waiting queue. Then wake up the process. Then the pick up and to enter critical section. Okay, so that is another solution, the alternative solution to address the problem of the busy waiting. So this is the prototype, the structure of the such a without busy waiting semaphore. So we can see the value will be minus. This is the same. However, so we can maintain the waiting queue. Then in case of wait, first the block. Put the process list. Probably it's the PCB. We are going to use the PCB, process control block. So process control block will be added to the any type of queue. Okay. Then in the signal, in case of signal, so if the value will be increased, then we can select one of the process, that is the wake up the operation. So this is the changing the wait and the signal operation using block and the wake up to address the problem. Yes.
Who is maintaining this list of processes?
Operating system.
Operating system.
Yeah, because it's operating system solution. Operating system provide such a data structure, so you don't have to implement block and wait or whatever. Just define code, just like the example in your program. You can just call this. In this case, it's named as SEM_wait, but it's a wait. Okay, so you can for the semaphore, so you can use
P-thread implementation.
I just copy and paste from the existing program. Let's see.
It is P-thread.
Yeah, I think that it's a P-thread because the name the P-thread create. So we are using the P-thread create the function, so system library. So we can use it.
My question is how the list is maintained. I mean, if we use the semaphore, the operating system will maintain the list for itself.
If you use I don't get your question. So
I mean, how we tell the operating system to keep the list of the processes?
By that in this case, where is the definition of the semaphore? Here, my semaphore. Yes, the semaphore is defined here. So that semaphore the data structure is already defined by the operating system as a shared library, so we can just code that define, then you use that operation. That's it, so we don't have to worry about it. Semaphore will maintain the queue in their structure, like this one. So in their structure, they add the queue inside the structure. This is still atomic operation. Okay. Okay, then you don't have to pay attention too much to this one, but we will see details about the deadlock. But when we are using the wait and the signal operation, as I said, the wait and signal with the mutex can be considered as the acquire the lock and release the lock. So if we have the two semaphore, then we have the two processes. So this is a timeline. So process 0, the wait the semaphore S, at the same time P1 wait the semaphore Q. Okay, this is the same time. They already got the they got the lock of the S and Q. However, what if the wait Q and the wait S? This should wait until Q is signal, and this one is to wait until S is a signal, which means this may cause the deadlock, the situation, deadlock event. We will see details about such a deadlock because the lock-based algorithm may cause the deadlock situation. So then also to address such a thing, the simplest way is that we can give the priority. Priority is not explicitly assigned a priority value, so we can consider a bunch of different the priority to address this one. Also, so we will see later. And however, any priority-based algorithm may cause starvation. Also, which means always the P1 may not get the resource, the semaphore, for example. So, but I will set aside the deadlock and starvation for later. I think the chapter 7, so we will discuss later. So these are the three main synchronization solution: hardware and software. And in your program, you can directly code it, or the operating system. You can use the data structure like the semaphore or the mutex to solve the synchronization problem. So there are three classical problems of the synchronization. Many of the problems in your computer system or the algorithm actually inherited by this one. So we will take a look at such a critical, the critical section problem. So one is bounded buffer. So do you remember that the beginning of chapter 3, so we have defined the producer and consumer for the communication. So it's a bounded buffer. So we define the buffer for the communication. So producer put the data into the buffer, and the consumer read the data, so consume the data. So we will see, because we have the multiple processes and share the data. It's a bounded buffer. So that is a race condition that causes a synchronization problem. So we will see how to address such a problem. That frequently happens. And the next one is a readers and writers problem. So we have in computer system a lot of input and output. Read and write the data. So read may be okay, not always, but may be okay. So for the shared data. Problem is when you write the data, that causes a problem. So a lot of problem in the operating system is actually the modeled as the readers and writers problem. The third one is, this is usually the two process cases. What if n number of processes, but we have the limited resource? That is the dining philosopher problem. So we will see detail what is the dining philosopher problem. First, bounded buffer problem. So bounded buffer problem, as we have discussed before, is a producer and consumer process. Then we have the buffer to share the data. So producer is trying to create the data, generate data, and put the data into the buffer. The consumer read the data. So at the time, so we are going to define, so we have the n by n number of buffers, okay? Then each buffer, each byte has 1 byte of data, for example, the one item in this case, which means we can use the reference or the pointer for each item. So anyway, it's the one item. So we are going to have the 3 semaphore in this case. One is the mutex. Mutex is the 0 or 1. is the binary, the semaphore initialized to 1. It will be used for locking. It's a key, okay? Key to use the buffer. And the semaphore full is, we'd like to see whether buffer is full. In case of a full, producer cannot generate the new data, right? Because of that, we have the semaphore that may need whether or not this is a full. And another semaphore is empty, to check the empty. So consumer need to check the empty before read. Because it's empty, so we cannot enter, the consumer cannot read the data. So for mutex log, is 1 means it's not, nobody wait, okay? It's available. So 1 means available, 0 is used. It's the wait, the operation. So it is initially set as 1. The full means, the full 0 means it's not, it's empty, okay? Full 0 means it's available. The empty n means is right now the no data. So then in case of n, that the consumer cannot read the data because it's empty. So we will see. So for the producer first need to check whether it's the producer would like to generate the data, right? Okay. Then when empty is set as checked whether buffer is full or not. So using the empty. So empty is initially set as n. Okay, so which means the n minus 1. Okay, if this is empty is 0, the producer cannot generate the buffer. Then after that, the mutex log. So if the producer get both the empty semaphore and the mutex log, then finally produce the data in the buffer. Once it is done, then release the mutex log. So then leave the critical section, critical region. So sometimes it's called the critical region. So and then the signal full. Signal full means so initially signal is the 0. Whether this is signal 0, then increase the value. So number of items will be managed by the full. Okay. This is will be used for current status of the buffer. This is the number of items. Okay. Then, at the same time, the consumer process can be defined as this one. So, using the mutex log, only one process can enter critical section, right? So using this one, so mutex log and signal mutex. Then the wait full is checking whether buffer is empty. Okay. So if this one is full is initially 0. So in case of 0, nothing you can read. So you cannot minus until the producer generate the data. If a producer generate data, it's a signal full will be increased. At that time, if that is increased, you can enter the critical section. Then after you read the data, you delete that item. Okay. Then the release the log and this one you take out the item. Okay. So this is the reason why we manage the two semaphore to manage the full or the empty is one is useful while the producer is the producing. Okay. Another one is used for the consuming. This is the bounded buffer problem. It's two process cases. Then second, the critical section problem is a readers, writers problem. So this is a simple rule. Reader, how many reader? So many reader can read the data. Okay. How many writing? Only one. While a writer is writing a data, the reader can read the data? No. At the time, no. The reader. So writing is called the exclusive log. Okay. And the reading is called the shared log. That's very important because the locking concept also used in the database also. So it's a explicit lock and a shared lock. Okay? So this is our condition for concurrent process. Writing is can both read and write, but only one process, and only read the data set. They do not perform any update. Okay. So we are going to allow the reader let read the data. Okay. So many process can read, which means we need to manage a number of process that would like to read the data, and how many the writing, we can use the mutex for the writing because it's only one. So until you got the mutex lock, you cannot write the data. So that's the idea. So that's the reason we need the read-write mutex lock. This doesn't have to be the semaphore, the counting semaphore. It can be binary semaphore, mutex lock. Why? Because once you got the lock, then that's the only process that can write the data. Okay. Then here we have another mutex for the reader to enter the critical section and the integer to manage the how many. This is not the semaphore. This is to manage the number of the reader. Okay. For the writing, it's simple. So because only one process can enter critical section writing the part. So we can only wait the read-write mutex lock. Okay? Only how many process? Only one because it's a mutex lock. So that once done, it's a signal read-write mutex. So you can use such a critical section solution for the writing. However, the reader may be the little bit more. So for example, this part is the reading the data. Okay? It's different from the producer and consumer. In producer and consumer both read and write. Consumer read, after read, delete the data. It means it's a writing. Okay, so that some of the students confusing. What if we have one reader, one writer? That's different from the bounded buffer. Bounded buffer for the shared data, the producer write the data. Even consumer read the data, then delete the data. That means it's writing the data. Okay, both of them are writing, so you need to have the exclusive, the lock, that is the mutex lock. But here, so it's different. Writing, yes, it's typical, the synchronization solution. However, we need to manage a number of the process, the reader using the read count. Okay, so before that, this mutex lock will be used for wait mutex and signal mutex to the overall the readers the process. Okay, then increase the read count. Then in case the read count is 1, it can also get the read write run. Okay, it can get, because nobody use that critical section, so it can also get the read write run. Okay, then the signal the mutex. At that time, because of this one, many process can enter critical section. Okay, the critical section is only for this part. Okay, to manage the number of. However, otherwise it will cause the count will cause the synchronization problem, critical section problem. So this part is the critical section only for this part. Similarly, the weight, the mutex, signal mutex, this part is the critical. Overall, for the readers, so this part is the critical section. So there are 3 critical sections in this algorithm. This part, and this part. So for this part, so we can, many process can enter the critical section. Then once this one is done, we can reduce the number of count. Okay. Then release the lock of the read and write. In case it's a 0, we can release because nobody used this one. Even though we need to release the read and write the mutex lock, and the weight and the signal to update the read count will be released. So this is the reader's process. Okay? There are several variations of the readers writers, but I'm not going to explain the details. But for example, only once the writer is ready, then it should perform the writing, which means the writing should be guaranteed. It's a first priority. In this case, the writing will be waiting until if there is the reader. Okay? However, in general, the database, for example, the reader cannot block writing. Okay? So that if that is the policy, like this one second variation, so once writer is ready, it should be performed right away. Then algorithm may be changed, but I think that you can modify the algorithm of the critical section solution to satisfy this one. So there are many variations for the readers and writers, depending on the requirement. Whether you allow the reading while the data is writing, or the reading is blocked, then they give the first priority to the writer, something like that. Okay. However, most of them cause the starvation problem because it will consider the priority for the writer. Okay, if you have the only writer, the process, the keep writing, the reader cannot read the data in this case, so may cause the starvation problem. The third one is dining philosopher problem. So this is a kind of the model of the algorithm or implement application, the model. Okay, not directly it's only the reader's writer or the bounded buffer. It can be used for the many of the algorithms. It's kind of a model. It's a classical model. The third one is many process cases. So let's consider we have the 5 philosophers. Each philosopher can do only, they can eat. Okay, either eating or thinking. So in terms of process, we can consider each philosopher, each person as a process. That process can do either processing, consume the resource, whatever the resource, or idle. Okay? So in this, the dining philosopher problem, so this process can do either only thinking or with the eating. Eating means use the resource. So what kind of resource? We have rice. It can be CPU, it can be the shared data, it can be whatever the resource. We have the rice. To eat the rice, I'm not sure how many of you are using the chopstick. So let's say that we need 2 chopsticks, definitely 1 chopstick. And it's not possible to eat it. So in my case, I do not use the spoon a lot. So I mostly use the chopstick. So we need 2 chopsticks. How unfortunately, each philosopher has only 1 chopstick, which means to eat a rice, to consume the resource, this one need. So for example, this is a chopstick for this process, process A, chopstick 0. So B, C, D, E. And this is a 0, 1, we number, E4. Then this processor need 1 more chopstick. This process cannot get the chopstick from here, from here. Only this one or this one from the neighbor. Okay? So that is the only problem. So why this is a critical section problem?
Because it has a deadlock situation.
Yeah. Because you have the limited resource, share the data, but to access to eat or rice, you need to get the chopstick. In the worst case, all process, all philosopher take their own chopstick first. Okay? Then, which means this one, this one, this one, this one, this one. Okay? Then, nobody can eat. They are waiting the other. It's the worst case. Okay? So, we need to solve that problem using critical section problem, using the semaphore. Okay. To do that, we will define the semaphore for each chopstick. Okay, whether this one is used or not. Okay, so we have defined the array of the chopstick initialized to 1 because used or not used. So we need such a binary semaphore. Is okay. Then, so this is there are several solutions. So we can. This is a first solution. This is a critical section. This is an entry section. This is an exit section. For to enter critical section, which means to in the right or to use the resource, we need to get my own chopstick. So wait, so lock and right hand side. In this case, the 0. If this one is a 0, 1, 2, 3, 4. It's a next. So next one. So that is I plus 1. You understand why we need this one? Because 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, modular, right? Fine. Okay. If, for example, nobody used the chopstick, so then this one wait for its own chopstick. So get the lock. Okay. So chopstick 0 is set as a 0. Then plus 1 is a chopstick 1. It's currently 1, so we can wait to get the lock. So this one will be set as 0. Fine. Eventually, the philosopher can eat the rice, and this process can use the resource. Then once it is done, the release mine and release this. Then either think or other the remainder section. Problem? Deadlock. That's actually not the deadlock. Deadlock means, so it's called the live lock. Not the deadlock, it's a live lock. What's the difference? It's very similar. Okay? Live lock is kind of sometimes when you are working in the hallway, so another person is coming, sometimes I'd like to give the way, so I move to this one. Then the other person move this. Then I move the right hand side. Then other person move. Keep moving. Left and right, right. That is called a live lock. Okay? So keep doing something. So this may, so when all the process hold, okay, their own chopstick, that is a deadlock. However, in general, this, so I get the lock, the chopstick, my own. Then check the next one, is holding. Okay, so leave this one and hold, leave, hold. So it's the spin. It's kind of the deadlock. It's called especially the live lock. Okay, so to address this one, this is a simple solution. But to address this one, so why don't we give the limit? Only one philosopher, one process can eat the rice. Okay, so to do that, we can simply define mutex law. Okay, those who are getting, so to eat the rice, okay, we have only one key to access the rice. So those who get that, the key can eat the rice. Okay, that makes sense. Then there's no problem with the live lock. So we can define the one more, the mutex lock, wait, and the signal. Okay, problem? How many processes? How many philosopher can eat?
One.
Only one. Actually, to maximize, two philosophers. Okay, because we have the 5 chopsticks, 2 philosophers can eat the same time. That is the maximize. You can maximize the utilization, but you can use only half, less than half of the resource. So that's the drawback of this solution. Okay. So we will see later another solution of the dining philosopher problem using the other data structure. this is a general problem of using the semaphore. Using the semaphore is very simple to program in your application, mostly high-level languages. High-level languages such as C++, Java, they provide such as the API to use the operating system semaphore data structure. However, what if signal and weight they are independent atomic operation. They are independent. They do not bother each other. It's not many the same. It's an independent operation of the semaphore, right? Which means you can signal mutex first. You can just increase the value. Then later, the weight, the decrease. You release the lock first, then get the lock. Or you forget to signal, or sometimes you forget the weight, or just the weight and weight. Then that may cause the problem. That happened a lot long time ago in the operating system. The developer, programmer, they need to put the weight, then signal. But sometimes weight. Sometimes you forgot. For example, the previous one, when we see this one, we forgot that this the signal for the axis section of this critical section. Okay? Then it's a keep locking. Then nobody enter. Nobody used the read count from the previous example. So this may cause a lot of problem that happened the old operating system. Like the Windows, the 95, the 3.1, because they from time to time pop up mutex lock problem. Okay, I have seen a lot. So at the time, I didn't know the why it's caused the problem. How can we solve the problem? The main issue is they are independent. They independent operation in the semaphore. Why don't we adapt the idea of the high-level languages like the class in Java or C++? In the class, you can have the class. What is a class? It's a data structure for your object, right? Then that has the constructor and also data and construct and number of operation. Why don't we manage? So we have the semaphore, then in the semaphore there are two operations. Why don't we manage such an operation and log everything in one data structure, high-level data structure, like the abstract in concept of the Java. So that is called the monitor. So this is a problem of using the mutex log or the semaphore. So if we misuse, like this one, this causes the problem. Okay, this is the same problem. So instead, why don't we manage so these are the operations that we are going to do. Then we have we have the weight and signal and everything. So that in the data structure that is called the monitor. Okay, it's a high-level concept of the synchronization problem. Okay, so only one process. If there are many processes like readers, writers, or the philosopher, the many processes, they are waiting in the queue. Okay, then only one process among them will be enabled in the monitor. Okay, then developer, they don't have to worry about the weight and signal getting the log or not. Only define the monitor. Okay, monitor is an abstraction level, so you can just abstract the monitor and implement your operation inside. Then automatically manage who will get the log by the operating the weight and the signal. Okay, then you don't have the developer. That is the reason. Sometimes when you learn the semaphore or synchronization problem, I never used such a thing explicitly. Okay, that's true because it's more and more is abstraction level, high level. The operating system or programming nowadays, high level program language, they are in charge of such a synchronization problem. Okay. So to do that, we have the variable inside the monitor. So, by the way, the monitor has a 3 parts. So share the data and their operation. Then the developer focus on to operate, read or write or whatever. Then the initialization code. So in this the structure, there are 2 variables. One is the condition variable. Then using each variable has a 2 operation, weight and signal. Then the monitor in abstraction level, they will manage automatically whenever user could read the shared data, it's a wait and get the log and the release the log. When you release the log with the signal, then select the process from the waiting queue, the next process. Okay, this is the entry queue. Then we don't have to worry about the pair of the wait and signal. So it's just simply the wait and signal are implemented as the high level abstraction level. Okay, so that is, yes.
I think it has the same problem as the semaphore because I have to call the wait and signal for my critical section basically.
Mm-hmm.
What if I have
operating
the same
system?
problem?
When for example, I'd like to read the data. Okay, share the data. To do that, from the previous example, we need to operate the wait. Okay, before we read the data. So wait the mutex.
In monitor, I have to do the same thing to.
Oh, you don't have to. You don't have to. That will be so. You need to manage the operation only. This is the same concept as the abstract in Java. In the abstract they implement then you can add when you define the class with the abstract. Okay, so then you can add your operation only. So it's the same thing. So instead of the implementing wait or the explicit wait and signal, you don't have to do in the monitor.
How do my process know that I have to wait for?
Then that is not your job. It's the operating system job or the API.
Okay, how does it know?
So I don't know. So it's implemented. If you want to know about the details, so that will be managed by the condition. The condition is the when. So for example, there's no the process in the queue, and then there's a process that define that called this monitor. Then this monitor read the data, that is the operation. Then automatically that the data structure, monitor structure will invoke the X wait. Okay. So condition.
Monitor has to call pulse all wait.
Yeah, monitor will call that wait. Then it's get the log and access the data. But then you don't know.
What if the developer do pulse
then
wait,
you do not use the monitor. Instead, you can explicitly define the semaphore, then the wait and the access the data and the release.
No, what I'm saying is I can have the same problem in the monitors that you explained in the semaphore.
What kind of a problem?
That I can call multiple times wait and wait. I don't call pulse at all.
Oh, you don't have to call. Monitor itself call when your operation is invoked. Why? Because only one process is enabled. The other process will be waiting. Okay, that enabled process, selected process. In your process, in your thread, so if you read the data, before you read the data, the monitor data structure will invoke X wait. Okay, that X is to maintain the processor. Okay. So using the condition variable in the monitor, so you can maintain the X and Y. The problem is when the signal is happen, so signal is operated, the next process will be selected depending on which process is selected. Sometimes it may cause the starvation, so it should be considered. Okay, such a high-level program language provide the monitor. So let's take a look at the example of the dining philosopher problem using the monitor. So we are going to use the monitor for the dining philosopher. There are thinking hungry means, in this case the hungry means so would write. Okay, would write to enter the critical section, and eating is consuming. And for the 5 philosopher, okay, so we define the 5 condition variable. So there are operations. So pick up and the put down. So pick up is the I can get the chopstick and the next one also. To do that, we need to check the test. Test is checking whether the next one is available one first. Okay, if yes, then we can get the chopstick. So then here this one is we can get the chopstick. This one is here the pickup. You can get the chopstick. Once you are done, we can release the chopstick. Use the put down. Okay. Then at the time, we need to always learn the test. Then we can solve the synchronization problem. Okay. So using this code, this is a driver code. In the driver code, when you pick up the I process, so for example, the first philosopher is a 0, pick up 0. Then if this one is done, then pick up this one. Then this one check whether next one is available. Okay, then the edit and the put down. Okay. This is another solution using the monitor. At the time, the variable is the mutex max. I'm going to skip this part. Then one of the issue is which will be selected from the waiting queue. Okay, so first come first server can be used, but not adequate. So you can provide a priority number for the process in the waiting queue also. Okay, so these are the overall the synchronization problem solution. So each and every the operating system has their own. It's based on this one. This the algorithm discussed so far is general. The critical section solution. So you can take a look at for each operating system how they implement. For example, Linux until the kernel version 2.6 they used only the disable interrupt. Okay, then the consume or the read and do the something operation, then enable the interrupt. Okay, then it will be solved. So from 2.6 they fully implemented the preemptive the synchronization solution, and they provide the semaphore and the spin lock and readers writers the version of the critical section solution. And also, as we have seen in the middle of the slide, so we have seen the pthread, the API for the synchronization solution. Okay, so that's the end of the chapter 5. And one more thing is I think that you asked the question about the quiz 2. This one? Yep. So I got the same question from the other student, and I remind that the last semester was the same question. So because I realized that if you search the Google, it shows the solution in the stackoverflow.com or whatever. Sometimes it says it's a six process. There's no problem to determine the processes. What about the thread? So how many threads?
8 threads.
8 threads? Yeah. Any other? 2? So what is the question here? Why do you think there is 8 thread?
Because each process has its own thread.
Okay.
And we have one fork in the child process, which creates 2 different
So
threads.
obviously we have the 6 processes. That's not a problem. Okay. Yeah.
And we have 2 processes in the child process, so which makes it 2 calls to the create thread process.
this one,
Yeah.
each process is a thread. So this one is the another thread and another thread, so 8 thread. What is the
Right.
question? The unique.
What is the
How do you recognize the
uniqueness?
unique? Using ID. Okay? So process, when you put the return of that one is the process ID, and also I do not specify because I do not specify the what types of the thread we use depending on the thread. So I just generate command to create a thread, like the p thread underbar create that return thread ID. So that is the reason. It's not just how many processes, not just how many threads. So it's how many unique process. It's how many the unique process ID and how many unique the thread ID. That is the question. If we generalize too much like the thread, so yarn is the thread. So okay, so that is the reason. The answer, the probably GA grade as the 2. I did the same thing last year. So if you answer A with the justification, like the describe why, because the question is the why. Okay, if you do not answer why, it will be the same. But
in the solution there is no explanation for why.
I'm explaining.
Yeah, but I think the solution.
So that solution sometimes not completed. Okay, so I'm providing, right? So if you specify the answer, the why, okay, justify, it will be the change it. Okay, so those who, however, the GA cannot check the all 73 submission again. So if you answer A with your justification, why don't you email to or send a message to the GA, check your quiz 2 again. Okay? But if you just answer the number only, which is the A, it cannot be the change it. Any questions? So why don't you email to the GA? Yes.
My question is, can you go back? Can you show the question number 2, please?
Okay.
Yeah. How many unique threads?
Okay.
How we are differentiating the threads uniqueness with their thread ID?
Process ID and the thread ID.
Thread ID,
Yes.
not the process ID.
Yes.
Because it's unique thread.
Yes.
So when I fork it, it will copy the complete process.
Oh, yes.
So when it's copying, the complete thread ID will be copied. Everything will be copied.
Yes.
So it should have the same thread ID basically.
Where is the thread ID?
It's in the process.
No
New process.
That has the process ID. Then create
It should
a
have,
thread.
it will have its own.
Why don't you bring your code or the proof? Okay, where is the thread ID in the PCB? There is no thread ID for the process PCB. It's only the process. Then when process create the thread, okay. In this case, the thread I know. If you consider thread as the sequence of the instruction, then process is a thread. Okay. But when we learn the thread, so it's the more specific. So thread is the shared part of the process instruction. So that create using for example the p thread underbar create, it return the thread ID. That's the unique thread. So that is the reason. It's a 2. However, I understand it's not clear. So if you answer the A, that consider where you consider the 6 of the process also the thread, then you will get the credit. Okay? You understand what I'm saying? So I understand, I agree. I do not decline your answer, but you need to justify why.
I explained it. You still didn't give me the credit.
Then I will change it. So why don't you inform to the GA? If you answer why, then you will get the credit. But I do not ask the GA to check the regrade all the thing. Just to inform. If you answer with your justification, then why don't you inform to the GA? Then you will get the credit. Any other questions? Why this is 8 and 2? Okay. Thank you. We will finish today 5 minutes earlier.